So let's get us some rules of logarithms that we can put to good use as far as helping us with some graphing stuff, helping us with some simplification stuff that corresponds to logs, and because of the simplification stuff, helping us out eventually with equations, so stuff that'll help us solve equations that have logs in them. We've got properties of logarithms, rules of logarithms, and with the way that things are listed here, the m, the n, the b are positive. B is not equal to 1, as we've been saying with our base stuff. X is allowed to be real, so wherever x shows up in any of our rules, that is allowed to be a real number. We've got things that are based on the idea that logs are equal to powers, like log base b of 1. If we take b and raise it to a power, how are we going to create the number 1? Well, the only way to do that is a power of 0. Log base b of b. What power on b gives us b? Well, the invisible power of 1. Log base b of b to the power x. What power on b gives us b to the power x? It answers itself, x. Because that gives us an x, that looks like an inverse sort of relationship, and it is. The other version, because we said that composition would have to go in both ways, if we take the x and put it on our base, that's one way to start. If we pick a number and put it into a logarithm first, well, we've got to pick the right kind of number. So it has to be a positive number. Put it in our log base b, take that new number and make it a power on the b, and that should get us back the original number we started with. So that's the logarithm version of our inverse rule. Because logs are equal to powers, there's a relationship between our rules for exponents and our rules for logarithms. If we have a product inside of a logarithm, we could split it as the sum of two logs. If we have a division inside of a logarithm, we can split it up as log of the top minus log of the bottom. Log base b of m to a power, well, shoot, if that power worked nicely when the bases were nice and the same number, does this work out in an almost kind of nice way? Sure does. That power can come down to the front while the rest of what's inside the log stays inside the log. And so what we've got going on, especially with these rules that are numbered 5, 6, and 7, we have these rules. They can be used in both directions, so we can use the rules the way that they're written as a way of expanding into a bunch of logarithms. So logs that are added together, subtracted together, logs that have numbers in front of them, so we can expand things. If we use these rules instead from right to left, then we can condense the group of logarithms into a single log. Depending on what we might want to do, we may want sometimes to expand, we may in other cases want to condense. So it all depends. It's just nice to have the tools if we come across an issue that requires them. So let's take a look at some examples where we expand. We'll do a couple of them that are already pre-finished before we do one together. We have inside of our logarithm a product. We've got some powers. Those powers are attached to individual variables. So we've got to do the product part, the multiplication part first, split the multiplication into adding logs. Then each of those logs still has the power on the inside. We can take the power from the inside and kick it to the front. Take the power from the inside, kick it to the front. If we have, there's division and a root in there, well, I want to remember that the roots are also connected to powers, but the division is the main thing to worry about first. I got to split the division. log of the top minus log of the bottom. Then I can change the root for a power of 1/2 and kick the power out in front. A lot more going on in this example here. Oh boy, we've got log base 2. Up on top, 3w squared x. Down on the bottom, 8 cube root of y. Well, if we start trying to handle things there, then we're going to start with the fact that there's division that splits the top from the bottom. Log of the top minus log of the bottom. In this first log, I've got multiplication inside. In the second logarithm, I've got multiplication inside. So I'm going to need to split those into separate logs that are added together. Log of 3, log of w squared, log of x. Those got to all be added together. After the minus sign, parentheses, because we don't want to forget and mess up anything. We don't want to mess up anything that has to do with subtraction. So after that minus sign, we are getting another logarithm that's being broken apart using adding. Log of 8 plus log of the cube root. Those are inside of brackets to make things a little bit nicer. We can distribute the subtraction. And we can then start talking about all those powers that are showing up getting broken out front. Can't do anything with the log of 3. The power of 2 gets bumped out front. Log of x, can't do anything with that. Log base 2 of 8, hey, wait a minute. 2 to what power gives us 8? 2 to the power of 3. So I can actually replace that entire logarithm with a 3. I want to make sure I'm keeping an eye out for those sorts of things. I don't want them sneaking something in on me, and I think I've simplified stuff as much as possible, and then they go, ah, we caught you. And, don't let them catch you. Keep an eye out for logs that have numbers in them. Log base 2 of 3, couldn't have done anything with that. Log base 2 of 8, can do something with that. The root gets changed into a power of 1/3. The 1/3 gets kicked out in front. Everything is expanded as much as possible. Going the other way is kind of like reversing what we were just talking about. So if we take a look at this example where we want to write things as a single logarithm, we're going to go, okay, I got numbers out in front. When I was expanding, that was the last thing I did. When I'm condensing, that's going to be the first thing I do. Then I'm going to try to put things together based on any sort of adding or subtracting. But I've got an extra wrinkle in here. 2 natural log of z, no big deal. Minus 4 natural log of y, no big deal. Minus 1/3 natural log of x, no big deal. Plus 2, I'm sorry, wait a minute. Where's the logarithm? Nah, that's the sneaky part. Like we were saying, watch out for logs of numbers that can be simplified. Now we've got to instead watch out for the other way. Watch out for numbers that need to be backed into logarithms. I'm going to need to take that 2, and I'm going to need to back it up into having a logarithm show up. So we've got to use one of our other rules for logarithms that says, hey, you want a logarithm, specifically a natural logarithm, then you're going to need an e inside of that showing up after that 2. Now you've got a logarithm to work with. Now you can do something with that 2 and combine all of the other logarithms together that you need to combine together. But again, we're going to start with popping all of those numbers from out front back inside as powers. So a 2 out front gets popped inside as a power of 2. A 4 out front gets popped inside as a power of 4. A 1/3 out front gets popped inside as a power of 1/3. A 2 out front gets popped inside as a power of 2. Some of those logarithms are added together and some of them are subtracted together. So if we pay attention to what's going on, we've got two of those logarithms that are added together. We've got two of them that are looking at minuses being in front. So when we start putting things together, because of that fact that there's some minus stuff, we're going to have inside of our logarithm a fraction. Now let's try to be smart about this. The stuff that is already positive is going to have to be part of that numerator. Because those are positive and also added together, I'm going to take those green underlined pieces and create that numerator. That's going to have a product in it because they're added together. The sneakier part is about the stuff that's underlined in red, the stuff that's both minus. Rather than having to go through some extra steps, I go, hey, if these are both minus, then I can go ahead and put things together by taking their insides and multiplying them together, because they're both negatives. I can multiply those insides together, but because they're both negatives, that multiplication goes down in the bottom. It's a way of dodging factor out the negative from both of those, then reassemble using that multiplication rule, then reassemble further by slapping that stuff in the denominator. So the shortcut idea, just to try to be a little bit more clear about it here, the shortcut idea is once we've got all of our coefficients put inside, any logarithms that are straight added together are going to create multiplication in the numerator. Any logarithms that are straight subtracted are going to create multiplication in the denominator. It's just a way to try to dodge extra steps of how that negative would have to get pulled back out for it to be put together and then put back together. Ugh. Trying to dodge that, trying to streamline things. Logarithms that are straight added together with no negatives in front of them create my numerator, multiply your insides together. Any logarithms that have negatives in front of them, multiply your insides together, slap them down in the denominator. This is some of the good stuff, but there's just a little bit more that we can do. And that has to do with what's called change base. One of the cool things about logarithms is that we can go back and forth between any kind of base that we might want. And that's especially helpful because, again, what we have at our disposal is the common log and the natural log. So if we really want to do stuff like calculation-based, graphics-based, we're going to want to use the common log or the natural log. So having a different kind of log, a log base 3, a log base 41, what? Not fun, not super useful. Being able to change the base into something much more useful, that's good news bears. So any logarithm can be changed to a different base in the following way. I can pick any base that I want, but on the top is the log of the original inside, and on the bottom is the log of the original base. So inside, log of the top, or log on top is log of the inside. Base, log of the base is on the bottom. Common log version, common log of the original inside over top of common log of the original base. Natural log version, natural log of the inside over natural log of the base. This gives us a way of taking care of things like the log base 3 of 17. I can't do a log base 3 on my calculator directly, but if I change to the log of 17 over the log of 3, or the natural log of 17 over natural log of 3. Challenge y'all to check that out both ways. Same value to 3 decimal places. Log of 41, log base 41 of 23, common log version, natural log version, either way. Take that, calculate it, round to 3 decimal places. You're going to get the same answer either way. Challenge you, check it out. Going back to that example from our previous discussion of how to graph logarithms, and at that point saying we can only do a sketch by hand. Now, change base allows us to take our calculator out, change that base to a common log or a natural log. So log of the inside, log of the base on the bottom. Log of the inside, log of the base on the bottom. The negative still stays out in front of those. The -4 still staying at the back end of things. Now we've got a version of things that we can type into our calculator. As long as we're careful about typing it into the calculator, we'll get that same graph matching up with one we sketched out by hand. So change base, also very cool, very helpful for us, giving us a little bit more graphing capabilities than just having to sketch things out by hand.